it's having geographical advantage what we are going to get due to moon. There's another thing. Okay, leave it. Artificial satellite. It's for communication purpose, for like a navigation purpose. We are using that particular satellite now. What all to predict the weather forecast? Now we do take help of the satellites only. So artificial satellites become very, very important. What all we have: mobile communication, DTH, television, everything revolves around the satellite communication only. It's one of the most important aspect here now. So without satellites, again, life will be a little bit difficult. That much I can say. So we are going to describe the motion of satellite around the Earth. Okay, let's take this day, planet Earth. Let it be some planet, and this is satellite. Mass of satellite. Let me take m naught, and it's going to revolve in a circular orbit. Now it is having orbital speed v naught. Now who will provide that required centripetal force? The gravitational attractive force between the satellite and the hub and the planet will provide required centripetal force. Sir, force is acting should move down. You go back to circular motion because of centripetal force and velocity v naught, tangential v naught. It is in circular path. Am I right? Because of these two only, tangential velocity and force, it is in a circular path here. I'll give. Yeah. Okay, now let's come forward directly. So F is equal to mv naught square by r. So what is smaller? R is the radius of the orbit. This is the orbit. And what is smaller? Called as radius orbit. V naught is orbital speed. What is this F? Gm m naught by r square. So solving for this, V naught equal to how much will get? Gm by r. So this is the orbital speed of the satellite here. What is m? M is the mass of the Earth, not mass of satellite, mass of the planet. What is smaller? Radius of the orbit. As the radius of the orbit increases, orbital speed decreases. I think this is very important. So those satellites which are away from the surface of the Earth, they will have less speed. Those which are nearer will have more speed. So the orbital speed depends on what? The radius. So as the radius increases, the orbital speed will decrease here. So I'm interested in the time period, time taken to complete one revolution. So for that, time taken to go around, this speed will be constant by v naught 2 pi r. What is v naught? V naught will be gm by r, or this will become 2 pi r to power of 3 by 2 by gm. So or square of time period is proportional to cube root of radius or cube of radius. This is nothing but Kepler's law of planetary motion. Tomorrow we'll analyze here in detail. This is the expression for time period of revolution. It's go round that one. Time period of what is the time taken to go round once, or it's a periodic motion. So the time period is given by this particular thing. Let's come for energy of satellite. What all forms energy? It's having kinetic energy, and also there's interaction potential energy. So the total energy should be equal to sum of potential plus kinetic. What is the potential energy is equal to? Minus G m m naught r. What about kinetic energy? M naught v naught square by 2. Let me substitute this m naught r. What is v naught? V naught square will become G capital M by r. So if I solve this, This one. So this is the energy of a satellite here. Agree this one? Oh no, how potential and kinetic energy are related? So shall we say that K is equal to mod of E? You look at the K is equal to mod of E and it is equal to mod of U by 2. Potential G is what? G mm naught by R. And what is energy is equal to? G mm naught by 2R. So for any conservative field, there is one basic condition that is applicable. The kinetic energy, total energy, and the potential. They'll be related by this. So same thing we are going to explore even in atomic structure. When we go to atomic structure, no, the same condition I'm going to take help of this one. There's the total energy of satellite. I got negative. What do you mean by that? If total energy of satellite negative, it will be a closed or elliptical orbit. We are discussing about the circular orbit here. So if an orbit, if you get total energy negative, no, then that particular orbit is said to be a closed orbit here. And what about this force? Is a central force and out acting along line joining the center of satellite to center of the planet. Okay, this is about the orbital speed, time period of revolution, and the energy of a satellite here. Okay, let's come for the orbital escape velocity. Will take this one. Next condition is mass of the planet, and here's what I'm taking a particle. So with what speed I should project so that it will escape from the attractive force of this one. Means after what should be the separation? It should escape. Escape means I'll show it to her. What is the separation? Separation will become infinity. There's a planet. There's a body which has to escape from the gravitational field of the planet here. Or here we are talking about very specifically the Earth. So what should be the escape velocity here? So for this, we'll take help of again the interaction potential. You know, conservation of mechanical Ui plus Ki, Uf plus Kf. Here, let me assume that it will come to rest at infinity. And anyway, the planet will be fixed here. No, I need to bother about kinetic energy of planet. It will be fixed here. Okay, what is the initial interaction potential energy? Potential on the surface minus gmr into m naught will give the interaction potential energy plus kinetic energy m naught ve square by 2. Initial final interaction potential energy 0. It will come to rest here. So if I solve it, 2g mr, I'll get it. M naught get cancels. And what is root of gm by r? Root of gm by r. Anything can we write it? Because we know small g is equal to what? G capital M by r square. So shall we adjust one? So root of this will become 2gr. So this is the expression for escape velocity, and it is for Earth, it is around 11.6 kilometer per second. So if you project a particle with that much of speed, no, 11.2, it will never return back over. If you project with a speed equal to 11.2 kilometer per second from the surface of the Earth, it will never return back. In terms of small g, I expressed here. In terms of orbital speed, what is the expression for orbital speed? Gm by r on the surface of the Earth. Okay, I think here only I'll introduce that. If there's a Earth, if the satellite revolves near to on the surface of the Earth, just above at a distance of 10 meter or something. Just you can take even 100 meter also we can take it. If it revolves on the surface of the earth with an orbital speed. So what is this orbital speed should be equal to? You can write only gm by r. So what is this orbital speed on the surface of the earth? So how this orbital speed on surface of the earth and escape velocity is related? So they're given by formula root 2 v naught. Now how it is projected irrespective of no whether you project at an angle, irrespective of that one means either you project it like this or you project it at an angle. So will it depends on that angle? No, it is independent of angle of projection. Will everything will make it for Earth? Any other planet? Okay, they'll mention it. No. So what is the thing? In both the cases, escape speed will be same, escape velocity, as it is independent of angle theta. Because the potential what you write minus g m naught by r no is anything theta will come in this expression, nothing to do no. And kinetic energy independent of direction. So either you project in either case or depend the speed required will be same. So there's no any restriction on what like the direction. Both the cases the escape speed will be same here. Like that, the escape speed and the orbital speed they're related by this. What is v naught? Not far away from the Earth. When the satellite is revolving near to surface of the Earth, near to surface of the, this is the orbital speed. Somebody. Okay, come for this one. Okay, this v naught don't get confused. Smaller I wrote. So where the orbit? Orbit lies near to the surface of the earth. And these are, I think, you have enough numericals to solve. So plenty of questions are related to this. Don't touch elliptical orbit. Tomorrow I'll discuss that. I'll finish off that. Then you can focus more numericals here. Okay, then so tomorrow you can focus on elliptical orbit. Today, later to this, you can go for it. Okay, let's go back to the some application numericals. If it is at infinity, if it is having some velocity, that you substitute here. Because usually I want it to escape to infinity, and at infinity, what will let it be at rest? I assumed it. If it is at infinity is having some velocity, that velocity you have to substitute here. Then calculate what escape velocity you needed. Let's come to the some questions. Read this one. I'll have water. Just read this one.